Hello.
Hi.
Okay, so we'll be starting then the event. So I'm Gediminas Pajera, and I'm a DPhil student in theoretical chemistry and also the events officer of Quantum Information Society. And I welcome you tonight to a long-awaited talk by Christopher Monroe. And this is actually one of our biggest talks this term. More than 100 people has registered for this event, and we almost reached full capacity. And yeah, so thank you for everyone to joining this talk. And before letting Christopher to present um, his talk, I want to make a quick announcement about the society and our upcoming events. So next week, we'll be having a question and answer session by Scott Aronson that kindly agreed to come and speak to our society members. So I will be sending a registration link in the chat. And if you're interested in asking anything about quantum information by Monroe, also leading researchers, and Scott Aronson, then please come and join the event. Also, if you're interested in our society and want to hear more, please follow our Facebook page and also check out our webpage. Although this term is almost at end, we'll be having many more different events about quantum information next academic year, and we'll be hosting a range of events from quantum computing workshops to speaker events like today. So please check them out, and we'll also post in the chat the links to Facebook page on our webpage. Also, if you have any event ideas, want to give a talk yourself, or want to contribute to the spread of quantum information, write us a message either through Facebook or through email, which you should be able to find in our webpage. Okay, so we are today joined by Professor Chris Monroe. He's a faculty member and a professor at University of Maryland and Duke University, and he's one of the world leading researchers in the field of trapped ion quantum computing, and he is a truly pioneer, being the first person to demonstrate quantum logic gate experimentally and first to use trapped ions for controllable qubit demonstrations. And also, he has done other things like his group showing uh, producing quantum entanglement between two widely separated atoms, and for the first time, teleported quantum information between matter separated by a large distance. Now he runs IonQ, a startup aiming at building a scalable trapped ion quantum computer. And honestly, I could talk much more about what he does and what he has under his belt, but today he will be talking about how you can use atoms, such a small and at first glance an interesting object, to leverage the bizarre features of quantum physics, such as uncertainty, entanglement, and measurement, to solve classically impossible computational tasks. It's really inspiring to think how much could a quantum computer change, but there's still a lot of research we have to do to get a fully functioning quantum computer. And I think that Chris Monroe is one of the people who's contributing heavily to this mission. So I welcome him and enjoy the talk.
Okay, thank you, gentlemen. Can you allow me to share screens?
Yeah, just a second.
That would be helpful.
Okay, are you able now?
Yeah. All right. Okay, how does that look? Okay.
Great.
Well, first, thank you for the invitation, and I'm delighted to to speak. I guess we're all getting used to this kind of this venue. It's a little strange, I guess, but the good thing is nobody can throw tomatoes and yell at me. The bad thing is I like to make eye contact to see who's really listening and so forth. But I understand that this is a pretty interesting group of folks from all levels. But so I'm here to tell you a lot about what you probably already know. But this is going to be a quantum information talk from a very experimental viewpoint. And clearly I'm going to be talking about this platform here, individual atoms as qubits. So this is well, it's not live, but it's a recorded image of about, I think there's about 20, maybe 25, maybe 32. No, sorry, I shouldn't count. it's between 20 and 30 atomic ions, each of them behaving as a qubit. And through this talk, I want to tell you how this works and what it takes to make a system like this. But my main job is still at the university. I did spend about a year running the company IonQ, but now they have a professional CEO running it, and it's a group of about 55 or 60 people that are making these systems, engineering them in ways that we can it's very hard to do at a university. I'll talk a little bit about IonQ, not too much, but more about the physics behind these atoms and some of the research we're doing and others in the field in this platform. Okay, so this picture here, these atoms are very cold. They're laser cooled. They're being suspended by an ion trap, which is a device that has a bunch of electrodes with electric fields, and the charged atoms feel these electric fields, and we can sort of make a bottle, make a three-dimensional confinement potential for these atoms. They're so cold that they're really small. They're pretty much pinned down to a few nanometers in space. Each of these blobs is about 2 microns across, and that's just from the optical diffraction. You're seeing an image of laser light that's scattering off the atoms, and we're collecting the light. And this is not quite diffraction limited. It almost is. You can sort of see the blurriness in some of these atoms. It's almost diffraction limited. The spacing between the atoms is about 5 microns. And that's a balance between their repulsion, their Coulomb repulsion, and the external force that's holding them together. And so from left to right here, it's on the order of 1/10 of a millimeter. So it's not really that tiny, but it's pretty small. And I want to tell you a little bit about this platform and how we can execute quantum gates and, in the end, run algorithms. So I take it most of you have a background in, you've taken a quantum class or two, and you've had other lectures in this series, and you're pretty well up to speed on the basics of quantum computing. Nevertheless, I want to maybe start with an introduction that is experimentally motivated. And it comes from what we now think of as the second quantum revolution, meaning that the quantum physics discovered in the 20th century is being mixed with information theory, also a 20th century thing. And information theory is maybe not as common, at least in physics circles, but this group probably knows more about information theory than I do. But I like to point out Turing and Shannon in particular in the mid-20th century, who in a sense made information theory abstract. They defined what a bit is, what information is. On the left there, the so-called Turing machine here, this abstract device that has a tape with a bunch of bits, and you have a head, and you can move, you can do gates between a memory on the head and whatever is in front of the tape, and the tape moves across the head that way. And the point of this Turing machine is that you can represent abstractly any computer, any classical computer with that model. It's a computing model. And even though no real computer runs this way, it was useful to formalize what a computer is. And then it motivated people to go out there and look for real devices that would behave as a computer. Shannon, for his part, of course, Turing in the UK, Shannon in the US, for his part, codified information in terms of entropy and made very profound connections between thermodynamics and information. And of course, the bit, the two-level system, is the fundamental unit of information. And this is his entropy, Shannon entropy formula. And what's important there, and Turing also used bits, is that once we understand information is encoded in bits, the task then is to go find bits in nature, switches of any sort, currents, anything, capacitance, charge on a capacitor, and really the story behind the 20th century computing era was finding bits in nature and perfecting them. And of course, this led to technologies at the time, vacuum tube technology. So these are sort of the first digital computers, the first one being in the UK, Colossus, ENIAC, shortly after that in the US, and And to show parity here, there's the Soviet Union's version in the late 40s, MESM. So these vacuum tube devices were able to store information in devices represented by these electric currents. Of course, vacuum tubes, these are pretty big tubes and they break all the time. Not a great technology to scale, although clearly they did that. They did exactly that. But along came the solid state transistor, which everybody, at least physicists, know this lovely picture from Bell Labs, the first solid state transistor. That dark thing on the bottom is a chunk of germanium, and there's a gold ribbon that is meeting with it. So it's a 3-terminal device, and you can see the 1 terminal right here, and one terminal here and 1 terminal there. And basically it's a current dependent current switch. And it looks pretty, it doesn't look very reliable. Certainly it doesn't look any better than in fact, the vacuum tube here looks more like a standard. This looks like a physics experiment. But because it's solid state, of course, it could be engineered massively. And that's really what happened in the era of Moore's law, where we saw the continual shrinking of silicon transistor elements down to nanometer dimensions. So this takes me to Moore's law. And I'm trying to motivate how quantum computing, some of the evolution of quantum computing is following history in a little way. We're kind of in the vacuum tube era of quantum computing where we're trying to find really good technology. So this is a recent plot of the last 4 decades of Moore's law. And it's a log linear plot, the number of transistors normalized to 1978, and the year on the x-axis. And I put this, you might not have seen this version, but it's starting to saturate. And I think we all know that our laptop computers aren't getting much more powerful these days. And it's because it's very hard to shrink down transistors more and more, partly because they're approaching molecular scales themselves. And there's not enough room. And you can't just make the chip bigger and bigger and throw more transistors on there, because there's all kinds of power dissipation issues and interconnection problems. And even the speed of light becomes a speed limit to do gates between delocalized transistors. So this brings me to Richard Feynman, one of our heroes in quantum information. And as early as 1959 at an APS, the American Physical Society lecture, he talked about, I think he was stimulated by these solid state transistors, and he was thinking, how could you really shrink those down to individual atom-sized elements? And he even said that when you do that, there will be, this is a wonderful paragraph. Yeah, he said there will be completely new opportunities for design. And he didn't know what those, nobody knew what those opportunities were. But he has a nose for physics and also for the advent of new devices. And when you change the rules, when you change the laws of physics that underlie something, there just have to be new opportunities. And that's really where he was coming from. And we now know, I think, that it's pretty clear that opportunity is quantum computing, and it took many years for that to happen. But again, pardon me for being really slow. I know you all know this, but in quantum computing, we take classical bits and expand them to include quantum bits that are allowed not just to be in the definite state 0 and 1, but they can be in superpositions of 0 and 1. So for instance, it's very hard to draw, but this single electron is actually in a superposition of 2 orbits. And if we can denote those orbits, blue or red, 0 or 1, we can have an arbitrary superposition of the 2 states, because that electron is a wave, it follows a wave equation and so forth. And so we write a qubit, the general state of a qubit, as a superposition with weights alpha and beta that are complex numbers. And of course, the laws that are so hard to conceive and sort of understand at their roots is the fact that when you make a measurement on a superposition, it has to make sense. In other words, we don't experience superposition, so we have to we sort of cook the books and interpret a quantum measurement as collapsing the superposition into a definite state, and those definite states have probabilities that are given by these weights alpha and beta. Okay, they're complex numbers, so we take the mod squared, and there's a Schrodinger wave equation that tells you how to control alpha and beta without measuring. That's important. The Schrodinger equation is easy in the sense it's just a wave equation. The measurement is also easy to describe mathematically. We use probabilities. It's not easy to understand, but I think one nice thing about quantum mechanics is I've never thought it to be really hard. It's just that we have no analogs in everyday life, so it's very difficult conceptually. I think that's sort of a misnomer. Many people say, oh, quantum mechanics is so hard. No, that's not it. It's just that we can't, you know, it's very hard to draw analogies from real life. Now, there's great things that happen when we put many qubits together. We get something called entanglement. And again, I assume this crowd has heard it and knows about it. This is an example of an entangled state of exactly 2 qubits. And sure, it's no problem to prepare 2 qubits in any superposition you want. But this superposition is kind of neat because when you measure that superposition, you find perfect correlations between the states. And this analogy of cubes that are drawn with ambiguous perspective is it's actually the only analogy I know of that gives a little bit of a flavor of entanglement. When you measure, when you look at an ambiguous perspective like these cubes here, you typically see one perspective or the other, but they're correlated. And that's an optical illusion that's playing the trick. But in real quantum entanglement, there's no illusion. It is that way, even if the cubes are really far apart. So I like to think of this as a little bit of a tongue-in-cheek comment, but entanglement is allowing qubits to be wired without wires. It's the structure of the quantum state that allows them to be wired. And that's really where all the advantages of quantum computing comes from, this entanglement. So it comes down to how do you, and I'll spend most of this talk talking about discussing how we generate entanglement and control entanglement. And of course, when we do that, we have to prevent measurement from happening, but then at the end of the day, we need to measure. So we sort of have to do it all in a very controlled way. Now, I'm not going to talk much about applications. I'm sure you've heard more about things like Shor's algorithm, and there are a few esoteric algorithms that take advantage of this entanglement. But that area of research, I think, is super active now. And indeed, we need more killer applications in quantum. But I would say one reason we don't have so many is because we're not used to the rules of quantum computing. And it seems that the applications in quantum computing are of problems that we don't pay attention to very much because they're really hard problems, like optimization. And that's the one thing you sometimes hear. And the reason I mention optimization is that when you put together lots and lots of qubits, the space grows exponentially, because with n qubits, you can have a superposition of 2 to the n states, and it can be an entangled mess and so forth. But if you want to measure the system, you really don't want all that entanglement when it comes time for measurement, because if you have just a superposition of 10 to the 100 states, when you make a measurement, you have to use probabilities to describe what that output will be, and that's basically noise. You really don't know what answer you're going to get in the end. So we look for algorithms, and I'm speaking very quite vague right now. We look for algorithms that sort of take lots of superpositions and they force them to a single answer, or the quantum state through interference and entanglement, we can somehow get a very simple state at the end. And the output, when we measure it, doesn't have so much entropy anymore. There might only be a few states remaining. And the best part is that result, when we measure a final result, it could depend on exponentially many inputs. So I mentioned optimization because that's one very general and important application where that's exactly what happens. Like this mountainscape here. What's the tallest mountain in the mountainscape? Well, you can just look at it and quickly see, well, it's this one. Well, we can look at it because we can plot the mountainscape. We can plot this landscape with 2 variables like longitude and latitude. And we can just look at the picture, and our brains are very good at just eyeing on the tallest peak. But if we have a function with, say, 10,000 variables, you certainly can't plot it. And there are exponentially many values of this function. What's the minimum value of this 10,000 variable nonlinear function? Those problems we don't tend to, we have approximations. They're very good approximations, but it's still, this is one of these exponentially hard problems, an NP hard problem. And it seems that quantum computers might be able to help us with those approximations. Now, I'm not going to get into the science of algorithms. I will issue this disclaimer. Nobody believes that a quantum computer can actually solve for the optimum value of a complex function. And there's some pretty deep reasons why, having to do with gaps getting exponentially small. Lots of, you could be fooled by having a false minimum, a local minimum, but it's not the global minimum. However, quantum computers do exactly what optimization routines need, and that is one answer that depends on all of the inputs. And it may be that quantum computers will form another level of approximation to optimizers. Hard to say. But this is sort of the culture in designing algorithms. There's not much of a culture in looking at optimization problems. We have our approximations, and again, I'm a little bit on thin ice. This is not my field. Those approximations are really, really good, but there are many areas in physics and logistics and other areas and other applications that are really slow. And one of them, close to a physicist or chemist's heart, is the modeling of electronics or molecular energy levels. Molecules, if you have 30 or 40 electrons on a molecule, those electrons actually do an optimization routine all by themselves. They're quantum objects already. And so the electrons, if you want, you can interpret a molecule as sort of a special purpose quantum computer for that molecule. Now, there are routines that map molecular structure problems onto a quantum computer. Again, this is also research, ongoing research, but it's one of the big possible applications in the future. Even this smaller molecule, this is caffeine. I don't know, I think it has something like 50 electrons, maybe 100, or yeah, it looks like it has a lot. This probably has about 100 electrons. We can't solve the ground state binding energy of caffeine classically. Now, maybe we don't need it, but for other molecules that could be catalysts, knowing the binding energy is really important to see how it reacts and so forth. This other molecule is it's even harder, but also much more important. It's called FeMoco, iron, molybdenum. It's a nitrogen, a molecule like this fixes nitrogen. It changes N2, the triple bond of N2, into ammonia, and it's used, you've probably heard the story, it's used for fertilizer. And we know that bacteria can do this nitrogen fixation much more efficiently than any artificial kind of man-made process. So what does that have to do with the traveling salesman problem? Well, the traveling salesman problem is a logistics problem, optimizing, for instance, this is a particular route through cities in the United States. What's the shortest route visiting each of those cities once? That's a classic logistics problem. Nobody believes a quantum computer is going to solve this problem, but it may give approximations that are better than the ones we have. Some people don't even believe that, but that's okay. We do need algorithms though. So now I'm going to jump into experiments, and the segue is this. It's very well motivated. A lot of it being so speculative, we kind of have to build things and see what they're good for. But my colleague Bill Phillips is fond of saying about quantum computers that, yeah. So here's the quantum computer. Anyway, it's a kind of a neat picture, but it's pretty weird looking. It certainly doesn't look like that laptop. And Bill is fond of saying that a quantum computer differs more from a laptop than a laptop differs from an abacus. And the reasoning here is that this laptop down at the bottom and the abacus are both Turing machines. They can both be modeled by this abstract model of a tape and a head. Whereas the quantum computer, you can't do that. It relies on totally different rules of physics. So the corollary to this statement to me is that why would we ever expect a quantum computer to be made of the same components that make a laptop? In other words, silicon. In fact, if you read between the lines in this lecture, I am a very harsh skeptic of a possibility of quantum computers to be built out of solid state. Now, we need solid state fab for almost everything around our quantum computer, but not the qubits. Yeah, right. Solid state qubits are just not very clean. And a lot of it's beautiful condensed matter research going on now, but they're not nearly at the level what we see in atomic system. Now there is a slight exception, I would say, and that is the use of superconducting loops. This is a very interesting solid state. Of course, superconducting loops for qubits, they can be unmeasured because they're superconductors. The current flows without dissipation, and they can inductively or capacitively couple to nearby qubits, and you can make a solid state computer that way. But it's actually not your typical solid state. Each qubit is actually really big, maybe 100 microns across. But so this figure here, by the way, I sort of stole and adapted from a review that the editors at Science magazine wrote many years ago. In fact, I had to add neutral atoms and photonics on the right here as possible platforms. These are sort of the leading platforms to build quantum computers, and they're all pretty exotic in their own way. I talked about superconductors, individual ions that I'll get to in a minute. Why are they exotic? Well, they're individual atoms in a vacuum chamber. We control them with laser beams. Individual spins inside silicon. Again, these are really noisy. Nobody really knows how to build one of these things. I think they need some fundamental breakthroughs in their devices to be able to do this. This is a beautiful idea. Topological qubits, you may have heard about it. It's sort of like the string theory option, if you want. It's, again, I can't tell if you're all laughing at that or not really happy there, but it's beautiful condensed matter physics, storing information in the topology, like a fractional quantum Hall type effect. Nobody knows how to build them, or much less put two of them together and build a gate between them. Although they're nice ideas and a lot of funding, like from Microsoft, going into this. Optical quantum dots in defects in solid state systems like NV Diamond, a very attractive platform. Maybe not for computing, more for communication. Neutral atoms are very much like trapped ions. They're a little bit behind because it's very hard. They're neutral, so they don't interact very strongly. So it's a little harder to engineer. And then all photonic systems, and they can take advantage of the fact that you can write waveguides on silicon chips and take advantage of silicon VLSI manufacturing techniques. Okay, so I'm going to talk about these trapped ions. In some sense, they are the most reliable qubit we have. These are individual atoms. They're all identical. They're actually very good atomic clocks. And unlike neutral atoms, and this is subtle, unlike neutral atoms, the qubit is inside each ion here, but the confinement of the ion is entirely independent of the qubit. We confine the ion based on its charge, but the qubit is based on some other degree of freedom, like a magnetic spin or something, or an electronic orbit. But the charge itself, the qubit comes along and there's nearly perfect common mode rejection. The qubit states feel the trapping force exactly equally, and that's why they make very good atomic clocks. Neutral atoms, actually, you can't do that. With neutral atoms, there's no charge. And so you actually have to distort the atom to create a dipole and make a dipole trap to store it. But there's always a systematic effect on the qubit. By trapping a neutral atom, you are changing the qubit. Now, there can be wonderful ideas on engineering that system, but nothing is more stable than an individual atomic ion. And of course, the ions can be trapped for long periods of time. This is a crystal of about 80. Yeah, this is 80, exactly 80 atoms, and they can exist. They can stay in a crystallized form for hours, sometimes days, if you're at cryogenic temperatures. This crystal is trapped on a chip made by Sandia National Labs. I think I'm sure the Oxford Ion Trap Group, one of the leading groups in the world, has one of these chips. They make their own chips as well, we know. So some of you have seen this. This bow tie thing has about 100 electrodes you can't really see, and these atoms are sort of hovering above the surface. This whole chip is about 1 inch across from left to right, the dark part, and it's all mounted in a chip carrier in a vacuum chamber. Okay, so I want to now dive down into the details of how we entangle atoms, make gates, and then come back out and talk about some high-level physics experiments, what we can do with circuits, and how we hope to scale up in the long run. Okay. All right, so let's dive in. A little bit of atomic physics. These atoms, by the way, they're glowing blue because it's actually ultraviolet, and this is a UV sensitive camera, so it's false color. But we shine light that the atom fluoresces with. And the great thing about individual atoms, isolated atoms, is that they won't scatter just any light. They scatter light that's tuned to about 9 digits of accuracy. So we have to have control of that laser beam. So those atoms are actually ytterbium-171. And why ytterbium-171? Well, that'll maybe become obvious in a minute here. But there are several atomic ions that are appropriate. The one used ones used at Oxford are strontium and calcium. At NIST in Boulder, beryllium, magnesium, mercury. There's a host of about 10 ions that work. What makes them work is something very simple. If you take an atomic ion, what we like is to have a single outer electron. In laser-cooled atomic physics, we have a very reduced periodic table. We like really simple atoms, like hydrogen, right? What could be simpler? We have 1 electron in hydrogen. So if you want to do a neutral atom experiment, hydrogen is great. The problem with hydrogen is that the first excited state is in the deep ultraviolet, and we don't have lasers there. So when you go down the periodic table, sodium, cesium, rubidium, you hear those all the time because they're infrared wavelengths, very easy to get. So with ions, the second column, the alkaline earths, beryllium, magnesium, calcium, strontium, barium, those are popular. Ytterbium is a heavy guy, but it also has 1 outer electron, it turns out, maybe surprisingly. But one really nice thing of ytterbium is the nuclear spin of this isotope is 1/2. So surprisingly, it's just like the neutral hydrogen atom, the quantum numbers. So we have a spin 1/2 nucleus and a spin 1/2 electron. So the ground state is a quartet of levels here, separated by the triplet and singlet states. And they're split by a hyperfine interaction, the spin-spin interaction between the electron, this outer electron, and the nucleus. And in ytterbium, that's hyperfine splitting is 12.6 gigahertz. I've spelled it out to 11 digits. We know it to 15 or so digits. This is a very stable frequency. Every ytterbium-171 atom is exactly the same. So we have a standard already built in the system. Furthermore, these 2 levels that we use as a qubit are m=0 levels. So they feel very little linear Zeeman shift. So that means a magnetic field won't shift the qubit. So not only are we isolated from the world, we're in a vacuum chamber. There's no surface, there's no solid. We're not sensitive to electric fields because the charge means that it's at a 0 electric field, otherwise it would move. So it's sitting here in 0 electric field, and it's not even sensitive to magnetic fields. So it's a really good qubit. In fact, it's these really are the best qubits we know. There are no idle errors of importance. That's important to know. This qubit will live as long as you want. Even this true ground state here won't decay, but even the excited state, it'll take 10,000 years for it to decay naturally. And all of the noise on this qubit is from our controls, basically our laser beams that execute logic gates, okay? All right, so there's the qubit. Now, the first thing we can do, and this is true in any atomic physics experiment, is that we need to be able to measure the qubit. And all the ions and neutral atoms in cold atom physics have a similar type structure. We take advantage of a so-called cyclic or cycling transition. And in this case, we're going to invoke the first excited electronic state, P1/2 state. And this is an optical transition here. And the important point is when we shine light at a particular wavelength, and again, you need 9 digits of accuracy here. This is in the near ultraviolet. When we shine light at that wavelength, it decays right back down. Now, in reality, it can decay to these other 2 states. That's a technical thing. We can clean that up easily. But the important thing is this state up here cannot decay to spin down. Only spin up will fluoresce and spin down is dark. And so this is data on the right here, where we have a single ion in the trap, and we shine light on it and collect photons. And we do it a few thousand times, and we get a distribution per shot of how many photons we got. And we get roughly 1 photon every microsecond. So the integration window is 50 microseconds, and we get about 30 clicks usually. But there's a Poissonian, actually it's even more than Poissonian. There's a width associated with this. Sometimes you get 20, sometimes you get 40, but we almost never get 0. And the point here is that if we're in the other state and we do the same experiment, this is exactly the same experiment. The only difference is that the atom is in the spin down state, the other qubit state. And you see, we largely see darkness, 0 photons. There's a little bit of stuff going on here, dark counts from the detector, cosmic rays, things like this, catastrophic events. But the point is, these two distributions are so far apart that we have really excellent detection efficiency. My colleague Jung-Sang Kim at Duke on hyperfine levels has, this is a few years old, but he's shown more than 3 nines of detection efficiency in a small amount of time. If you have a different configuration, you can get even more nines. Rainer Blatt's group at Innsbruck has demonstrated that. Also, the group at Oxford are pioneers of getting very high detection efficiency. So this is sort of, it comes for the ride. If you have a trapped ion, then it's a very good detector, and it's highly coherent. Okay. Now, you might argue the more important thing we do with this qubit is the coherent manipulation. It allows us to do gates and make algorithms. This is afforded with laser beams again. This time, these laser beams, this is a little more subtle than just scattering light and catching photons. This interaction is dispersive. It's not absorptive. It's dispersive because the laser we apply is far detuned from any excited states. So the atom is sort of like an index of refraction, if you want. When we shine 2 laser beams that are really far detuned, but their beat note is very close to the qubit frequency, and their beat note is coherent. These are 2 coherent sources. Then we can drive a 2 photon transition that's coherent. It's just like applying microwaves at 12.6 gigahertz, like doing NMR if you want, using optics. The reason we use optics is that we can focus the beams down to hit individual atoms. You can't, it's very hard to do that with microwaves. Also, as you'll see in a minute, we need to push the atoms around. We apply a force, and microwaves don't give much of a force because their wavelength is so long. Now, this is actually the main reason we chose ytterbium, is that the best wavelength to do this type of dispersive interaction turns out to be, this is a little bit technical, but magic wavelength for ytterbium is 355 nanometers. And that's important because this laser is a commodity. This laser is used for lithography of CMOS masks, and companies make very high quality and very well engineered lasers that have only one adjustment, and that's the on button or the on key. You turn it on, that's it. And a laser like this works for 2 or 3 years without thinking. You just turn it on. Now it's UV, so it's kind of a pain that you have to worry about, cleanliness and things happen, but that's kind of technical. But we don't have to worry about lasers anymore, which is great. This laser is also pulsed. It produces a frequency comb, and I won't get into details, but we shape, we control the frequency comb so that we can drive qubit transitions by using different teeth of that comb. Okay, so this is some really old data, but it sort of, with a single line, it illustrates the combination of perfect measurement, very near perfect measurement, and very near perfect coherence. It's just a Rabi flopping experiment. What we're going to do is prepare the qubit. Sorry, I've changed notation. Instead of spin down and spin up, we have 0 and 1. We prepare in the 0 state through optical pumping, and then we turn on this 355 laser for a certain amount of time, and then we stop, and then we measure. And then we do it again and again, but we don't average the measurement. We just measure once. Did you get lots of clicks, lots of photons, or did you get 0? And we put a discriminator in the circuit that says, okay, that was bright, that was dark. And so we can map that measurement onto a 1 or a 0. It's like tossing coins. Did you get heads or tails? And this is what the data looks like as we increase time. So this is coherent Rabi flopping between the 2 states. And it's pretty boring looking data. You can only have heads or tails. You can't flip a coin and get a 1/2. But what you see is that the coherence of the superposition is reflected in the noise. If you have an even coin, when you flip it many times, you're going to see that sometimes it's heads, sometimes it's tails. But if the coin is always heads, there's no noise. Now, if you do signal averaging of that signal, you get something like this, which is what you might normally associate with Rabi flopping. But again, the combination of near perfect measurement and very high coherence you sort of see right away. And any good qubit, you should be able to take data like that in any good qubit. Okay, so now I'm going to move. This next slide pretty much tells you how we entangle ions, and it's a little bit of a back of the envelope approach. There's some approximations in here, but it gets the basic idea across. So I just showed you how we can do single qubit gates, rotations, and so forth. How do we entangle ions? Well, we're going to take advantage of their collective motion. The Coulomb interaction is very strong, and if we push one ion around, all the other ions are going to know about it. Now, their qubit states won't necessarily know about it. Only their positions will. So we have to map the position, we have to map the qubit inside the atom to a position of the atom. And we do this with a so-called spin-dependent force, a state-dependent force. And this, again, is what the main use of those 355 nanometer beams in ytterbium. Again, you can use other wavelengths for different ions. But what I'm drawing here is this single ion here is either pushed up or down, depending on its internal qubit state. And this can be done through selection rules and looking at the atomic physics. It's actually not hard to see that you get a push or a pull depending on what state you're in, due to the energy difference and also the selection rules of your laser beam. When we do this to two ions in the chain, something very interesting happens, because in general, if the atom is in a superposition of qubits, it now is in a superposition of positions. And that's exactly the mapping we need to make entanglement, because if you think about the two states, the definite states up, up, and down, down, where they're the same, they both move up together or they both move down together, and their Coulomb interaction doesn't change at all. But if they're in the opposite states, up, down, or down, up, then their Coulomb energy is a little bit lower. There's a defect, and it's actually a dipole 1/r³ type interaction. These are very big dipole moments. We're taking a single charge and separating it by 5 to 20 nanometers. So that's actually a very big dipole moment. And so we have basically a dipole-dipole interaction. We're engineering dipoles here. Now, in terms of quantum information, if you look at the four possibilities of those two qubits, as I just said, the down, down, and up, up state don't feel any change in their Coulomb energy, but the other two do. And when you change energy in quantum mechanics, that's a phase shift. And so this phase shift here is the same phase, because it goes like the square of that distance. Doesn't matter if you're up, down, or down, up. And because there's no sign change between up, down, and down, up, this is a nonlinear operation. Can you see that? This is a nonlinear operation, because what happens to up, up is not a product of down, up, and up, down. Okay, and when we set that phase to be pi/2, that's as expressive as this controlled NOT gate. It allows you to do full entanglement when you add rotations, single rotations. Okay, that's how it works. And the rudiments of this approach were first proposed by Serac and Zoller a long time ago in 1995. And the version I'm showing you here, which it's a refinement largely due to Malmer and Sorensen, but also Solano and Jerry Milburn and so forth. And there are many other, many extensions of that, but that's basically how it works. Now, two simplifications I made. One of them is pretty minor, and that is we don't do this gate in the Z basis. In other words, the force is not in the bare qubit basis, it's actually in the transverse X basis of the qubit. In other words, this spin-dependent force depends on whether you're in up plus down or up minus down. So it's different. That's the Malmer scheme, but the physics is really the same. It's just a change in spin basis. The gate times, they're not super long. Sorry, they're not super short. They're on the order of 100 microseconds or so. And by the way, I never told you that the vibrational modes of motion are more like microsecond periods, megahertz type frequencies. So the gate is actually a lot slower than the normal modes. So that's a problem, because I ignored all the other ions in this treatment. But again, I was trying to just give you the general physics. I'll talk about that in a minute. The fidelity of such operations, they're basically among the best fidelities in any platform. Not surprisingly, these are trapped ions. And I will give a plug to the local crew that they've really set the records in 2-qubit gate fidelities, somewhat exceeding 99.9%. Admittedly, those are experiments with exactly 2 qubits and no more, but it's important to know that we don't really have fundamental limits here. The fundamental limits are well beyond 3 nines even. So it's a really promising platform to think about scaling. Okay, what about those other ions? That's sort of the second simplification I made. Right, when you do this operation, it's like plucking a guitar string or something, or a bunch of pendulums connected by springs. If you wiggle 2 of them, it's just a mess. And that's absolutely true. Unless you do it really fast. We don't do it really fast, so we have to deal with all those modes of motion, and that's really there are many different approaches there, but we can deal for small numbers of ions up to maybe 30 or so. We can deal with all the modes of motion. It sounds complicated. It's not so bad. If you get more than 30 or 40 spins, it turns out the modes become more local, and you can ignore the effects at the other ends. So it's like plucking a guitar string at 2 places, but if you pluck it in just the right way, the rest of the guitar string really is not excited. Now that sounds kind of awful. You have to do all that classical control. But this is what we do in atomic physics. We move all the hard stuff away from the qubit. We have a perfect qubit. All of the hard stuff is the control. It's not the qubit itself. We're never going to improve the qubit. So we have to improve the engineering of the controllers around it. And another point I want to make, you see this 1 over r cubed here. If we're going to be controlling all these normal modes, the normal modes don't have a 1 over r cubed. We have an all-to-all connection here. So by dealing with the normal modes, we now have a fully connected quantum computer. We can do a gate between any 2 qubits without paying any price. And that's not true in any solid state system where they have nearest neighbor interactions. And there's a huge penalty in propagating entanglement over the size of a big system. This is something the solid state community has not addressed one bit. They talk about throwing millions of qubits together, but they don't talk about the fundamental scaling issue of doing that. If they want to reach across that chip, they're dead out of the water, okay? And that's not true in ions. Now, with ions, it's hard to scale, no doubt about it. And I want to talk more about that in a minute. Time is moving along. I was going to get fundamental on you, but I'm not going to. I'm going to skip over a few slides. These slides, you can see, I'm going to skip through here. They tell you a little bit about how we generate that spin-dependent force. And I kind of apologize. I kind of wanted to do that, but I'm going to jump into the high level here. And this is a schematic from a few years ago of a system we built. It was supposed to deal with up to 10 ions, but the ion trap electrode, one of them busted, and it's still under vacuum. And it worked for 5. We're working with 9 right now, but it's taken many years to get there. But even with 5, when we started, what was interesting about this experiment is that it was a system. It was the first system I've ever been associated with, meaning that we didn't have to tweak every mirror all the time. Once we line these things up, all right, we have a laser beam here that's split up with a very fancy switch where we can individually address, sorry, I'm on the wrong screen. We have the laser beam here that allows us to individually address any of these ions, any pairs of them. And this multi-channel acoustic modulator has a bunch of radio frequency inputs. So it becomes a control problem of RF to do our quantum computing gate. And then when we want to measure, we can collect the fluorescence on a multi-channel, put a multiplier tube, as I mentioned. And it's important to know, even just with 5 qubits, we can do all 10 pairwise gates in this system. And what was a little bit of a surprise, I guess, in this experiment is that once we tuned it up, it would run for many hours without any calibrations. Things were stable enough. And again, the fidelities were 98, 99% or something. So we started looking at running small circuits, and we got an appreciation of the computer stack. Not just the hardware at the very bottom here, but all the way at the very top, we have these algorithms expressed in C-naughts and Hadamard gates. We have to convert them to our native Ising gates, we call them, these Molmer-Sorensen gates. We don't have Hadamards, we have rotation gates. And then we have to laser pulse shape, as I mentioned, to pluck the guitar string just right. So there's a lot of control going on here. And we had to do a lot of interesting stuff in making algorithms, compress them so that they can run faster. And again, because we have a reconfigurable, fully connected system, there's lots of power in this upper level of stack. And I have to admit, some afternoons we were forgetting that we were doing atomic physics. That was at the very bottom. And that was kind of neat. We're starting to appreciate the higher level system aspect of this device. Starting in about 2016, these collaborations started happening out of the woodwork. People would, IBM put their system on the cloud right around the same time. They had 5 qubits also, coincidentally, but their system couldn't touch ours in terms of performance. Their clock speed was a lot faster, but clock speed, if you have 5 qubits, clock speed never matters. Our performance is way better than the IBM system. So it was kind of nice because lots of folks from universities, national labs, even companies would come to us with, oh, we'd love to run this application and so forth. And that was a challenge for us because we didn't really have an API. We didn't have a cloud service where anybody could use the system. So these were true scientific collaborations. And one of my favorites, I want to talk about it briefly, is this one, quantum scrambling. It was with a collaboration with Norm Yao and Benny Yoshida. So you may have heard something about the concept of scrambling. Quantum scrambling is sort of like entanglement at all depths. So it's not just simply entanglement between all the qubits, but entanglement that has high depth to it. And it actually came up first in the context of black holes, which are thought to be fast quantum scramblers because a black hole is a closed system. So I guess that means you can describe it quantum mechanically. And people like Lenny Susskind and John Preskill really pushed that kind of interpretation. And there's this holographic principle that says that even wormholes can be thought of as entanglement between 2 black hole edges. And it's pretty out there stuff. And we certainly knew nothing about that. But one thing about this list of experiments is that it's like going to school again. It's super fun. Most of these are condensed matter simulations, but this one, there's a circuit they identified that we should run with 7 qubits. And the idea is we're going to test whether a given unitary, and this is a unitary that we apply, it's a circuit, does it scramble or not? This is a property of any unitary. Does it scramble or does it not? And you need at least 3 qubits because 2 qubits, scrambling and entanglement are the same thing because there's only one kind of entanglement. But with 3 or more qubits, there's varying depths of entanglement. The idea here, and this is, again, I'm even shy to mention black holes because it's a 3 qubit black hole if you want. And we have to apply, you'll note we have to apply U and its inverse, it's U dagger, its adjoint. And so we're actually evolving a system forward and backwards in time related to these out of time order correlators. But this experiment is super clean in that you'll note the input states. We have an input qubit here, all the others are zeroed out. And basically, if U scrambles, then this state gets teleported from qubit 1 to qubit 7. And it's seeded by entanglement between the black holes, between the unitaries. And then it's also post-selected based on a successful Bell measurement. That's important because if U and U dagger aren't perfect inverses or there's decoherence, it won't affect the teleportation fidelity necessarily, but it will affect the yield of the post-selected process here. So it's sort of an unambiguous litmus test for scrambling. It doesn't, and other tests are sensitive to those things. So for U, again, you can barely see this here, but the circuit we used, it's a general circuit. You'll notice there's parameters. There's a parameter theta here. And when theta is 0, it doesn't scramble. When theta is pi over 2, it scrambles. And so this is the observed teleportation fidelity that we see as we vary the amount of scrambling. And indeed, it goes above 1/2 when we expect scrambling to happen there. It doesn't go all the way to 1 because there's actually a lot of gates in this circuit and they're not perfect. So I guess I'll leave it at that. It's you can look at this reference up here if you're interested. I want to spend a few minutes before kind of closing down on a different set of experiments that they're not circuit-based quantum computing experiments. They're more quantum simulations. Now you remember we're poking atoms with lasers. Well, what if we poke them all at the same time? It's actually a lot easier in the lab, right? We don't have to have individual addressing. We can just have one big fat laser beam. And I love that because the alignment's a lot easier. And you get something interesting there. We get basically an icing model. It's in this icing model, and it comes straight from the physics I told you before. Remember, we had icing gates, but this is a fully connected icing model, and it's long range. That's the important thing. The distance between ions I and J is related to I minus J with some correction factors, but the icing interaction falls off with a power law in distance, and that power can be tuned between 0 and 3. 0 is actually not very interesting because that means it's all on all. It's a uniform, and you can apply mean field theory usually. 3 is not all that interesting either because that means it's almost only nearest neighbor, 1 over distance cubed. But we can vary that power law between 0 and 3, and that's sort of a neat knob to have if you want to study a phase transition, for instance, while varying the range of the interaction. And of course, with long range interactions, you have all kinds of weird things going on where information propagates much faster than it would if you only had nearest neighbor interactions. These so-called Lieb-Robinson bounds are modified and so forth. Now, this experiment, these sets of experiments are done, they're done with normal modes, but we're deeply in the dispersive regime where the normal modes are barely tickled. So when we pluck the guitar string in this experiment, we're barely touching them. And so we can adiabatically eliminate the phonons if you want. That's the kind of the jargon there. The phonons aren't part, it's a pure spin model. For quantum gates, as I was telling you earlier, we actually do excite phonons, but we take care of them. We make sure that they're disentangled at the end. Here we can run sort of in an analog mode. We can run this Hamiltonian. We can also add a transverse magnetic field, and it's not a real one, it's an effective magnetic field. This is just spin flips along the y-axis of the Bloch sphere. And what's important is that this spin operator does not commute with the icing operation. And so this is, in fact, this Hamiltonian is the simplest Hamiltonian that admits a phase transition. So because of the long range interactions, the nature of that phase transition is interesting. And there's all kinds of condensed matter physics-y type things you can think about. And I won't have time to talk about any of them but one. And I wanted to talk about this so-called dynamical phase transition. And in this experiment, there's our icing model. We tuned the exponent to be about 1. So it's a long-range icing model, and there's a competition between B, in this case, the transverse fields along Z, and the icing couplings that are along the x-axis. Now, this is a quench experiment. We prepare all the spins along the x direction, so up plus down for all of the spins, and then we turn on this Hamiltonian for a certain amount of time, and then we measure along the x direction of each and every single spin in a single shot. And depending on B and J, the behavior is quite different. I mean, if B is really big, what happens is the X magnetism, we're polarized along X. I keep using the wrong screen. We're polarized along the X direction. And if we have a big magnetic field, they're just going to precess around the Z field. We'll see oscillations. But if J is really big and they're along the X direction, not much happens because they're already along the X direction. But the X ordering will take over from the magnetic field. This is not a ground state because we're quenching in essentially infinite temperature. If we're up plus down to the nth power, that's almost like infinite temperature. And so when we measure, these are measurements for different values of B over J. As I said, when B is big compared to J, we see the precession along the magnetic field. It sort of dephases. It sort of dephases because J is not exactly 0. But when B over J is much smaller, we don't see much going on. There's some wiggles, but the evolution, I mean, not much is happening because the B field is too small. But I wouldn't say there's a phase transition here. It's hard to, I mean, there's kind of qualitatively different evolution here. But we can measure more than just the magnetization. This is basically, we flash the measurement light and measure the total brightness of all the spins. We can measure correlators. So this is an average of all two-body correlators. This time we're plotting the two-body correlator versus B over J for different numbers of spins. We actually see a dip. The dashed line is mean field theory, and the solid line is DMRG. And we see the data kind of has a dip, and that dip gets a little sharper as we add spins. This is 53 spins in a big chain. But again, we expect a logarithmic divergence in the infinite size limit, and we're not even approaching that. This is just barely a hump. So we can measure more than just two-body correlators. We can measure n-body correlators. So this is a very strange order parameter. We're measuring the mean of the largest domain size, where all the spins are in the same level over a huge, over a big chain. And as we increase B over J, we see there's a minimum domain size at some intermediate value of B over J, and then it comes back up. And this is data over many hundreds of runs for different values of B over J. And this is much sharper than we would have expected. And I guess the thing I want you to take home is with 53 qubits, we can't calculate where that kink should be. Doesn't mean somebody can't calculate. So I guess we can't call this a quantum supremacy experiment. This is back in 2017, because we can't prove that somebody can't compute this, but we certainly don't know how. Okay, so I'm really running out of time, just a couple of slides left. I wanted to talk about scaling in this platform in trapped ions. And again, I think the big picture, even though this picture should scare you, if you look in any AMO laboratory, the beautiful thing about these qubits is that the scaling is really not quantum. It's all about the classical controls. And yeah, they're pretty obscene. This is a picture of an ion trap with this was actually the lab where we use photons to communicate between two different ion traps. But you can see that most of the real estate is devoted to laser hardware and so forth. Well, we've spent much on one of our projects the last 4 years or so engineering that system to this. And without much exaggeration, everything you see here, not the students, but everything else you see here was crammed into this box that has about 1 meter on a side. There is some other stuff running around. You can't see 32 individual cables in the back, but this allows us to control up to 32 ions independently. And this is a schematic of that. We're using this Sandia trap. That's where that picture is taken. And we basically split up our 355 beam into 32 individually addressed and fully controllable laser beams, as I pointed out earlier. So this is the latest version. And this technology that we designed, most of the people on that experiment went over to IonQ. And of course, the company IonQ is they've built several systems of this type. You can see a little bit of the guts. This system's been retired. They have 4 systems at IonQ. They're building 3 more this year. And I guess what's cool is that we can actually engineer it so that we can run this thing remotely inside the box. And this is from IonQ. This is loading exactly 24 qubits. We actually load in a different part of the chip, and we move each atom that's loaded one by one. This is real time, and not all attempts are successful, but we can see when they are. You can see they zigzag. The crystals actually zigzag for optimal loading, and then we bring the chain up and focus down and ready to go. A chain in IonQ systems and also in our university system, they last, a chain of 24 ions will last probably a good half hour, 45 minutes. But the loading is really, really fast. And so that's sort of good news. Now at IonQ, they're not necessarily doing research like we can do at the university, but they are interested in metrics and running kind of textbook algorithms on their system. This is just a recent example. This is a 20 qubit a Bernstein, actually it's 19 qubit Bernstein-Vazirani plus 1 ancilla qubit. And it requires that 1 ancilla qubit be very well connected to the others. And so I won't get into Bernstein-Vazirani. It's an oracle algorithm that sort of, you hide information in the circuit. In this case, the information is a 19-bit string by the 1 1 0 1 0 1 1 1 so forth. And the question is, in a single measurement, you can tell whether you can measure what was in that circuit in a single measurement. And what's cool about the BV algorithm is that it's not a, it only involves Clifford gates. So in a sense, it's easily simulatable, but it gives you a good figure of merit for a complex object like this. Did it work or not? In each, with 19 qubits, there are 500,000 possible oracles. We didn't run all 500,000, but we ran many thousands, and we can sort of test the connectivity. We can move the ancilla qubit to be any qubit to test the, the connectivity of the system and so forth. So we're busy developing standards based on sort of textbook algorithms. We've also run some very simple simulations of molecular variational eigensolvers. You may have heard of this, and we're kind of tackling the water molecule there. And again, this reference can tell you a little bit about that. So, I want to, since I'm still low on time, I want to move on and talk about scaling. Well, one way to scale an ion trap, and this is largely due to, Dave Wineland and I thought about this a long time ago. In fact, let me change the color of these to white so you can see the references. Sorry. The idea of doing a computation on a small selection of ions and then moving ions through a very complex chip. And this is from 20 years ago, the Nature paper there. And there are some ideas on, again, we're making the controls harder. We're making the ion trap design harder, but we can scale up in a modular way by having different zones. And on the left here, even in a single zone, if you were able to say put 1,000 ions in a linear trap, you can think about having this looks like a Turing machine. Actually, you have a head of laser beams and a tape of atoms that you move around deterministically, and you don't have full connections anymore, but you end up being able to do this computation that way, shuttling. Now, another way to shuttle, I wish I had more time to talk about here, and this is a true modular connection over long distance, is to use photons. Again, here you might have a chain of a bunch of ions, and one of them is a communication ion that allows you to share entanglement with another ion in a different trap, even off chip, through optical switch work. And again, the physics of how this works is well known by now, and it's been copied in many different platforms. Trapped ions first, and now even superconductors use this. And the idea is that this is a heralded scheme where you try to generate 2 photons from 2 separate ions, and when you do generate 2 and they interfere, you can detect when that happens, and by detecting certain correlation events in these detectors, you can know when these are entangled. And the state of the art when we started this, the rate of entanglement was super slow. It was 0.001 hertz. Every 10 minutes we could entangle one pair, and now things are really booming here. I think largely led by the group at Oxford. This is just great for the field that we're making the photonic connections so fast. Well, a few hundred hertz, but it's going to get to tens of kilohertz in coming years, and then it becomes comparable to the Coulomb interaction and very usable for a scalable device. And I think the group at Oxford, our group, and others are really pushing on this direction. Okay, this is, I think, my last slide. Stepping way back, all right, I've certainly been very keen on trapped ion quantum computing platforms, but whatever platform you have, you need lots of qubits, and you need a correspondingly number of gates, right? If you have 10 to the 7 qubits, but you can only do 1 gate, that's totally useless. That's up here. If you have 2 qubits, but you can do 10 million gates, that's also useless. That's down here. And so this pink region is simulable. I borrowed this picture from Hartmut Neven at Google. This is the quantum supremacy line, where you can't classically simulate what goes on if you're up and to the right, and we want to be up and to the right. Now, it's the unfortunate fact that with current solid state systems, including superconductors, they are going up with qubits, but unfortunately, as they go up, they're going to the left. And when they make their systems bigger, each individual component performs worse. That's what we've seen so far. So this is not a good way to scale going up here. I don't care if you can put 10 billion qubits on your chip, they're going to be bad qubits. So with atomic systems, ions in particular, I think we really have the promise of dipping through here, eventually getting to error correction, which I didn't talk about whatsoever, because with ions, we don't need error correction, not for a while anyway. We think we can get to on hundreds of qubits with tens of thousands of gates, and that would put us sort of in this green land where maybe there's treasure, using Hartmut's line here. So sorry, I went a little over. That's the last of my slides, and I just wanted to show pictures of the group. We're outside of Washington. And yes, I am taking the show to Duke University in about a year, although I will still have a presence on Maryland's campus. INQ will stay in College Park, but I'll be moving to Duke by the end of 21, I think. That's how it's going to go. And this is a picture of folks at INQ. It's an old picture, about 50 employees there right now. So thanks. That's all I have.
Okay, thank you very much for your really interesting talk. It was really informative, and I hope everyone learned quite a bit about quantum computing. If you have any questions to Chris, post it in the Q&A section, and we have a bit time, as much as Chris can be here, to answer them. Just for the start, I just was wondering myself, could you talk more about your group plans to use microwave trapping in your work?
To use
microwave trapping.
Oh, trapping.
Yeah.
Let's see. I'm not sure what you mean by that, but I can take a guess. I mean, I didn't talk about the ion trap at all, really, right? I showed the electrodes, and we apply voltages, electric fields, to hold these ions. It turns out these traps are called radio frequency traps, and it's because you can't confine a free charge using static electric fields only, because you can't have a divergence of the electric field, basically. So in practice, we create a quadrupole field. So it's in 2 dimensions. We have a trap in 1 dimension, but it's an anti-trap in the other dimension. And by rapidly reversing the polarity of that quadrupole at RF radio frequency rates, you end up getting a real trap. It's called a radio frequency trap. It's not exactly microwave. It's typically 30 megahertz or so. So it's kind of lower frequency. So there's RF in the trap. And now we can use microwaves to manipulate the quantum bit. And there are proposals out there to not use lasers at all, but use microwaves for everything. And that's very interesting. And the problem is, remember, you need to apply a force to these atoms. You need to push them around. And when you do it when you apply a force using microwaves, you need a field gradient for the force. And with microwaves, field gradients are not very high because the wavelength of the microwave is long, and you can't focus microwaves very easily. So laser beams have very high gradients. The dipole force from a laser beam can be huge, and that's what neutral atom platforms use. So, there are many groups out there that are investing in microwave type gates, and the great thing there is you don't need a laser to do the gate. The hard thing is we don't yet know how to apply sufficient forces that don't also melt the entire apparatus, because you need a lot of power. So, once again, that's an engineering issue. And I think, maybe in a few years, we'll have some breakthroughs on the ability to engineer low loss microwave type traps. And so we don't do any of this in my group, but we're certainly well aware of some of the groups across the world, some in the UK and at NIST in Boulder, up at University of Oregon, David Alcock, who did spend some time at Oxford. So it's an active area. Winnie Hensinger down in Sussex, I know he's really pushing on that too.
Yeah, thank you for answering. Yeah, I was exactly mentioning that. So we have our first question by Max Abitwall, and maybe he wants to ask the question himself live. I just invited him to speak, so if Max, you can speak. Wait. Sorry, sometimes errors happen. Okay. How about now?
Hello. Can you hear me?
Yeah.
Okay, great. Thanks so much for the talk. So, sorry, I'm not an expert in the field, but can you explain a bit more about the systematics, whether they're instrument or sort of atomic physics based, that make it difficult to increase the number of qubits or gates for these ion-based quantum computers?
Mm-hmm. Okay, systematics. Where do I start? Let me start with one that sounds kind of boring.
Okay.
And it has to do with, these atoms. We can make a crystal be very long-lived. It can stay there for a long time. So what limits that? Well, the main limitation is actually the level of vacuum. The atoms actually suffer collisions with the background gas. And we can actually calculate that. That's one of the few collision theory problems you can solve in 3 or 4 lines. It's called a Langevin collision. What happens is the ion has an electric field, of course. It has its own electric field. Let's say we have a single ion. If there's a neutral atom around, and it's usually hydrogen, H2, in an ultra high vacuum system, this is usually hydrogen. Well, hydrogen sees the electric field and it gets polarized. And therefore it has an attractive force through its dipole moment and the electric field. And the reason there's an attractive force is the electric field from the ion falls off like 1/r². So it's an attractive 1/r to the 4 potential. And I didn't want to get into so many details, but when all is said and done, in a room temperature system, if you're at UHV pressures, the collision happens roughly once every hour per ion. So with one ion, in fact, it's fine. Every hour you have a collision, but in a more subtle detail there, with one ion, even that collision is not a big deal. It makes the ion heat up, but it immediately, within a few milliseconds, we have it back. So every hour you miss a few milliseconds, which is no problem. Now, if we have 60 ions in a line, every minute, some ion feels a collision, and it's like all the dominoes fall. Usually what happens, if one of them gets jarred, the whole crystal melts. It literally melts, and it forms a very hot crystal. And most often, we just lose the whole crystal. And it's because of these RF fields. It's a highly nonlinear driven system. So it's very hard at room temperature to deal with more than 50 qubits. There are a few other trap geometries, like a penning trap. I didn't talk about that, but that has its own problems. They are all spinning all the time. But in these linear traps where you have a line of ions, at room temperature, you're kind of limited to about 50. Now, you can go to, one way is to lower the pressure 3 orders of magnitude. Wouldn't that be nice to just turn on a button? Okay, pressure 3 orders of magnitude lower. Well, that button is to cool everything down to 4 Kelvin. When you go to cryogenic temperatures, not 40 millikelvin, like you need in all solid state quantum computing experiments, 4 Kelvin. So just a helium cryo system. When you get down to 4 Kelvin, everything sticks to the walls. Even the H2, even the hydrogen doesn't really cause a problem. And even if there's hydrogen or helium in the vacuum chamber, it has very low energy. It's at 4 Kelvin. It kind of bounces off these ions. So we have one cryogenic experiment, and we can load crystals of 200 ions, and they stay there forever. We never see them. In fact, I should show you a picture. We have a picture of about 120 ions, I think, and there's one gap. There's one hole. It's a different isotope of ytterbium, so it's not glowing, but it's there. It's like a toothless, missing a tooth. But that gap never moved over the whole day, meaning there was not a single melting event. So all right. So I answered you on one systematic, and that is scaling will require cryogenic temperatures. Now, here's another systematic. We're dealing with this right now. For these big chains, it turns out to put more and more ions in the chain. You remember I showed you when we load, they form a zigzag in the middle. Well, to get rid of that, you have to just relax the axis of the trap, and it gets weaker and weaker. Now, the problem with doing that, when you have lots of ions and you have a weak axial trap, is that they become sloppy. It gets harder to keep them really cold along the axis, and we're shining a laser beam in here. Remember, we're relying on individual addressing, and if the ions are fuzzing out, that causes a systematic error in all the gates that we do. And I also note that the very weak axis of motion gets hotter and hotter over time. It heats from noise on the electrodes. It's a classical effect. Now, make sure that you know that this doesn't affect the qubit. The qubit's great. Even if the ion moves, the qubit's fine. But when we map qubit to motion, the motion is all hot. That's a problem. So it's another source of control noise if you want. Now, the answer out there is we can put multiple species ions in the trap and do something called sympathetic cooling. And I hate to call out, well, I love to call out Oxford all the time. They're again, one of the leaders in using mixed species ions in a trap and doing sympathetic cooling to quench the motion. And the reason you have to do that is that you can't do laser cooling and maintain coherence of a qubit. Laser cooling involves scattering light. It's a measurement. Laser cooling is a measurement. But if you put a different species in there, it's not the qubit, it's sort of just a refrigerator. It's a different species, so the light that you use to cool that species doesn't affect at all the qubit memory, okay? So putting all of this together, doing multi-species with big chains in a cryogenic apparatus, nobody's done that yet. But we know how to do it. We know every piece of the puzzle. And this is something you can't say about other platforms. We really know what we need to do to bring this in. It's not cheap, and it's just painstaking stuff. And there's not that many groups out there like there are doing superconducting qubits or even neutral atoms.
That's great. That sounds really exciting. Thank you.
Okay, we have quite a few questions. So if we can we answer them a bit quicker so everyone can have a chance?
Yes, we can.
Not everything, yeah, but like all the people are interested to hear your opinion. So I invited Peter Spring to ask his question himself. So are you here,
hi.
Peter?
Can you hear me? Okay, yeah, great. Thank you very much for the talk. So my question is, I'm just interested, what limits the 2 qubit gate times that you reported that were like sort of 10 to 100 microseconds? And are there any kind of ways of maybe performing faster 2 qubit gates in these systems? Thanks.
Yeah, good question. There's a natural timescale for these gates that's given by the vibration frequency of the phonons. In this case, they're transverse modes. They're typically a few megahertz. But the period of a few megahertz is just a microsecond or so. Why are we 100 times slower? It's more, I guess, there's no need to go faster right now. If you only have 10 qubits, let me give you an example. And this is sort of a high level philosophical view. It's not going to get into the physics so much, but if you only have 10 qubits, you probably don't need to do more than 100 gates, maybe 500 gates. If you only need to do 100 or 500 gates, speed is just not an issue. Okay, so that begs the question, well, what if you have 1,000 qubits and you need to do 1,000,000 gates? It's always better to be faster, that's for sure, and it's going to become more important. The good news is that with ions, the fundamental speed limit is the Coulomb interaction. The Coulomb interaction is really fast. Well, it's the speed of light over a tiny distance. That would be a speed of something like 10 to the minus 14 seconds or something like that. And we're at 10 to the minus 5 seconds. So that's 9 orders of magnitude away. But the good news is there are protocols, they involve, I like this trade-off. By making the gate faster, it's a more complicated protocol for plucking the guitar string, plucking the ion. It requires ultra-fast pulses and really good control of those lasers. That's not quantum, that's all about classical control. We had a project a few years ago that worked with individual pulses. And once again, I'm not doing this to kiss up to Oxford, but they did a wonderful experiment last year showing gates that were a few microseconds. And they start to see fidelities go down because they're encroaching upon the vibrational period. But you can even go faster than that. And they know that as well, of course. It's just a different protocol. So the good news is we just need better laser tech. And the other last thing I'll say, I'm trying to wrap this up, is that our current experiments are in the ultraviolet. And there's not much tech. There's not much optical tech in the ultraviolet. By going to a visible qubit like strontium, calcium, barium, it opens up the door to all kinds of technology. So I think the best is going to happen in the future, and we'll be able to do faster gates. I think nanosecond gates are going to be really tricky. You need a lot of power for that. But I think few microsecond gates are going to be, are going to be with us in a few years. Thanks.
Great, thank you very much.
Okay, then there's a question by Shaba, and I will. You want to ask the question yourself?
Yes, can you hear me? Yeah, sure. It's a quick question. It's just about you are mentioning that you are trying to increase the ion remote entanglement rate from like 100 hertz to tens of kilohertz, and my question is, how are you planning to do that? Thanks.
Okay, the easy part of that answer is go to an ion that has more friendly wavelengths. And again, one of the main differences between our early experiments and the recent Oxford experiments is they did that. They went from UV to near visible in the strontium atom. It's blue, 420 nanometers, something like that. You can also go further, longer wavelength to barium. We should be able to go faster than that. When you get longer wavelength, you can couple into a fiber a lot better. We have to have fiber optics, by the way, because the interference, we don't want to be sensitive to misalignments of those photons. The atoms tend to drift around, and we want to filter that out through the fibers. So you have to couple into a fiber, have good detectors, and I think we can get to above a kilohertz by using the same tech we have now. No integrated optics on the chip even, but that will be the next step. Putting cavities or even just passive reflective optics that are integrated on the ion trap chip itself should get us to many, many kilohertz, I think. So it's easy to throw out orders of magnitude, but 7 years ago, we were 10 to the minus 3 hertz. Now we're at 10 to the 2 hertz. That was 5 orders of magnitude. And all we did is use better detectors, collect light more efficiently. And there are other protocols that are used in the NV Diamond platform that we can use as well that don't involve 2 photons, but 1 photon that we can think about. And that'll further increase things. There's a lot of, again, the point to take home with this ion trap technology, there's a ton of technology trains that are coming on, and we know what they are. They're not breakthroughs.
Thanks.
Okay, so you mentioned the Oxford team quite a lot. So there's actually a person from it, David Lucas, and he has a question to yourself. So
I didn't know you were there, David.
Hey, Chris, can you hear me?
Yeah.
Good to see you. Well, firstly, thanks for a nice talk and for all those plugs to the Oxford team. Guess I should return the favor for anyone who didn't pick this up earlier, that Chris and his team are the people who really pioneered a lot of these techniques. But I wanted to ask a question, more of a kind of high-level question, and maybe on behalf of my undergraduate students and so on who might be watching, is, whether, obviously an important question for them is whether to go into something like trapped ion quantum computing or quantum computing in general for a PhD or future research. So I wonder what your opinion is on where do you think the space is for future research in university labs compared with versus spin-out companies or versus national institutes?
Really good question. I think about that a lot, sort of existentially. I think about that because it's true. I'm involved with this company IonQ, but honestly, I don't. That's not my work. I love seeing it happen. Honeywell, a big American corporation, also has a big ion trap group. And the great news in ion trapping labs is that if you get an ion trap PhD or even a master's or bachelor's, you probably can get a job at one of these places, or national labs. But the question remains: if these deep-pocketed efforts can build systems that we can't touch, and I see that all the time myself. What's left for universities to do? Well, there are 2 ways to answer this. One is, well, we can try to do fast gates. Companies aren't going to do that because it's too researchy, things like that. There's lots of atomic physics things, storing 4-level systems instead of qubits, right? And the nice thing about that type of research is that a company, there's no way they can touch that. They just can't. They need to build systems, put them on the cloud. That's the big pressure these days, get on the cloud. But that's related to my second answer as well. If you have an ion trap system available on the cloud, and they will be, IonQ systems will be available before the fall, I think, on both Microsoft and AWS systems. I think Honeywell will also be part of AWS, so you'll be able to use these on the cloud. cloud quantum computers are going to be dumb terminals. They're going to be very high level APIs. You can do C0 gates, you can do Hadamard gates or something, but that's it. And if you use the IonQ system, that C0 gets converted into, I don't know, 3 or 5 Mulmer gates and so forth. You're not going to be able to run very deep circuits. So research machines will allow the users, including us and our collaborators, to get down into the dirty part of the system and re-engineer the system as it pertains to a problem. And the buzzword for this is called co-design. And companies just won't do it. And I say that from firsthand knowledge. You know, IonQ is not going to waste time playing around with fast gates. They need to get their system on the cloud. They need to get users. There's revenue, actually. You know, so this is a business model. And yeah, it's a really good question, David. I think about this pretty much daily on, you know, what am I going to do over the next 5 years with all these industrial. I think it's the best thing that could happen for research is having a dumb terminal out there. If we want people to use ion trap quantum computers for some standard non-researchy application, they should use the cloud. But if they want to encode a spin-1 system to study some topological edge state in a spin chain, they're going to have to come to university, because to do spin-1 requires totally different optics, and a company is never going to let you get in there and play with optics. They don't want to either. They want to close the box up, put epoxy around it, and have it sealed. So I'm actually pretty bullish about the leveraging the cloud service to help us do our research.
Okay, and we have a perfect question for the end. It's quite short, so I will say it myself. How do you envisage this field or quantum computing in 10 years? And what are your opinion about it?
My colleague Bill Phillips likes to say, well, it's a 50-50 situation here. There's a 50% chance that we'll factor 50 numbers in 50 years or something like that. I don't know. I have to say, the business side of things, and I've seen enough of it to, you know, when you give a talk in front of venture capitalists, that's not the talk I just gave here. I'm not saying you have to lie to venture capitalists, but you have to show that, you know, there's going to be something at the end of the tunnel. There's a path to something. And in research, fortunately, we don't really have to do that. It just has to be interesting. And I think in 10 years, this field will be live and kicking. It'll be super strong. Even if there's no killer app that you know, Shell Oil is going to you know, throw out hundreds of millions of dollars at. Even without that, I think it's still true that there are problems out there that are hard. They will always be hard for classical computers. Unless somebody proves that a quantum computer can't touch classical algorithms in all its domains, the field will be with us because there are problems out there that classical computers will never touch. I've sort of moved away from physics in the last few years, but at the high level, we come back into physics, like scrambling. I mean, that's cosmology, for God's sakes. So through the back door, I think our quantum systems can come back into research and do physics, maybe not atomic physics. I mean, we'll always, in my platform, you know, David and I will always be doing atomic physics, but at the end of the day, we're doing something at a higher level. And I think that research will always be there. And so I think, look, if you're a graduate student or a postdoc, man, take a risk, do what you want. Who cares about jobs? You're going to have jobs. You'll get jobs later, no matter what, even if it's not in quantum. So have fun. If you like it and you think it's promising, I would say go after it.
Okay. Again, our society really thanks you for giving this talk, and I hope everyone enjoyed listening to you and your research on.
Oh, thank you.
So
and
again,
I'm impressed by your efforts to put together your society. It's a great community in quantum at Oxford.
yeah. Okay, so sadly it's the end of the talk. So again, thank you and have a nice day.
Okay, thank you. Bye-bye now.
Okay, bye.